Hello, it's Dr. White. I'd like to give you a little background on the string problem that we worked on. What we wanted was something that people could actually see and get their hands on, and something that we could solve with continuum mathematics, and then compare it to solving the same problem with particle modeling techniques. The two students working on this was Billy Fournier. This is a picture of Billy. I think he plays at GTC 14. He's now working at Northwick Grumman, and this is Robert Pierce, who's now working at Raytheon. So we went to Walmart, got a bungee cord, got a couple of C-clamps, clamped it down, got a high-speed camera, and took a picture of it. So this is what a string actually looks like. So remember what this looks like. And then we took some measurements and solved the partial differential equation. I don't know if you solved the damped wave equation. I mean, it's not easy. It's not terribly hard. But it'd take probably a senior mathematics major or a first year in graduate school before you have enough mathematics under your belt to be able to solve it. It's about 20 pages of crunching, and then you got the initial conditions to put in to crunch out. And then we solved it using particle modeling techniques. Now, it takes a pretty sophisticated amount of mathematics to be able to solve this, but a freshman with one physics class, maybe one calculus class, and a little bit of computing skills can solve the problem using particle modeling techniques. And so what you do, you weigh the bungee cord, you decide how many particles you want to use, divide the weight of the bungee cord by that many particles, and that's the weight of each node. And you connect each node with the spring, and there you've got your problem. So if you can solve the spring problem, which most freshmen can do, and have some programming skills, then you can solve this guy. Now I'm going to run a simulation solved with this technique, and a simulation solved with partial differential equations. Now, if you notice the simulation done with partial differential equations and continuum mathematics, this kink in the string never goes away. And in the real string, it had this kink maybe in one oscillation, and then it got rounded out and disappeared, more like what our particle modeling solution looks like. And you see the particle modeling solution is much more realistic and way easier to solve if you have a GPU to accelerate your in-body code on. Now, this next simulation, we reduced the tension and ran another simulation with reduced tension, and here's what it looks like. If you notice the action in that string, and it can even go and cross each other, which you can't do with partial differential equations. You can't get this much action. So this was just a project to kind of show what particle modeling is, and that it's, in many cases, it's much more effective and much easier for students to solve. In a lot of continuum mathematics, you can set up the equation, but then you can't solve it, and you have to discretize it and solve it on the computer anyway. Thank you.